all. I am Astha Parashar.
I am Anisha Kause. Welcome you all in the behalf of IPS Academy Institute of Engineering and Science. We are gathered here for special 6-day event faculty development program on design and simulation of next generation semiconductor devices and its application. Now I request Professor Rupesh Dupe sir, head of the Department of Electronic and Communication, to enlighten us.
Actually, I didn't have prepared any speech, but then too, I could recall my days when I joined this institute. At that time, Dr. M.G. Sharma sir was the director of this institute. तो हमें सैटेलाइट कम्युनिकेशन दिया गया मुझे कि रुपेश यू टीच सैटेलाइट कम्युनिकेशन. So in the meeting I said all okay, but I went to him कि सर वो तो मैंने पढ़ा नहीं है सैटेलाइट कम्युनिकेशन. I didn't have got teaching of in BTech. Sir told me engineering definition. Sir told me definition of engineering is this only. You take up a challenge, you go on with it. तो इसे चैलेंज लो एंड मूव इट. फिर भी मैंने बोला सर तो एक गाइडेंस एक किक स्टार्ट तो चाहिए. सो ही सेड दैट यू ऐसा करो तुम डॉक्टर व्यवहार के पास चले जाओ. आई वेंट टू व्यवहार सर और व्यवहार सर ने बड़ा अच्छा किक स्टार्ट दिया और उन्होंने बोला तुम लोगों के लिए अपकमिंग इंजीनियर्स के लिए बस यही एक है कि मैं तुम्हें बुक्स बता दूं, जनरल्स बता दूं और एक फ्लो बता दूं. सर ने बताया और अल्टीमेटली इस लेवल पे पढ़ा कि वो एक टीप प्रैट करके एक वैली पब्लिकेशन की बुक आती है, उसमें भी एरर्स थे तो वो मैंने आइडेंटिफाई करे, मैंने पुटअप करे तो वहाँ से काफ़ी अप्रिसिएशन आया. यस यू हैव आइडेंटिफाई द एरर्स एंड द नेक्स्ट एडिशन वी विल रेक्टिफाई इट. So I consider engineering education to be this only, to take up challenge and move forward. I say to my students also कि भाई वो ऐसा होता है कि जो academics है it is always and always far behind the industry. तो ये बात तो श्योर है कि इंडस्ट्री में जैसे जो जाता है he takes up new challenges, new assignments and finally copes up with that and gives shapes to the reality. With that notion, design and simulation of next generation semiconductor device and its applications one of the most important topic as government of India is investing trillions of dollars on semiconductor industry. I am very much sure the person who will excel out with this kickstart, it should be taken up as a kickstart कि भाई हमें रेफरेंस बुक पता चल जाए, जर्नल्स पता चल जाए, एक थोड़ा सा एक व्यू पॉइंट पता चल जाए रिसर्च का, एंड रेस्ट ऑफ द थिंग नीड टू बी टेकन अप बाय अस ओनली. If people over here will take it up as a challenge, I am very much sure कि भाई वो भले ही वो कोई भी एज ग्रुप हो, भले ही हम एकेडमिक्स से हों, पर इंडस्ट्री में इतनी सारी जॉब वैकेंसीज इस पर्टिकुलर फील्ड में ओपन हो रही है, इतना बड़ा होराइजन ओपन हो रहा है that we can also find a little space either in industry or anywhere, that means in research also. Fine. So with that notion, I congratulate कविता मैडम. हुआ ये था कि भाई वो हमने तो क्या किया कि मैडम आपको देख देख के प्रपोजल भरा, आपका एक्सपर्टाइज. और यूँ कहा जाता है कि भाई जैसे अगर गाइड अगर बेटर हो तो शिष्य भी अच्छे निकलते हैं. तो कविता मैडम के जो पेपर्स हैं हम सभी में अच्छे, काफ़ी अच्छे पब्लिकेशंस लेवल पे हैं. वैसे क्या होता है कि मैंने देखा कि ये जो मटेरियल फील्ड है, इन दिस मटेरियल फील्ड वी गेट गुड इम्पैक्ट फैक्टर जनरल्स. क्योंकि अल्टीमेटली मटेरियल्स आर द वन विच आर बीइंग यूज्ड, तो लोग ज़्यादा से ज़्यादा रेफर करते हैं, दैट रेजेस द इम्पैक्ट फैक्टर. सो विद दैट व्यू आई अगेन कॉन्ग्रेचुलेट कविता मैडम. और वो पूरी टीम को तो है ही, सारे लोग यहाँ प्रेजेंट हैं, तो ये सारे लोग भी कॉन्ट्रीब्यूटर्स हैं. सो विद दैट नोशन आई स्टॉप माई कन्वर्सेशन ओवर हियर, क्योंकि मैं की नोट स्पीच का मैं जैसे जैसे बढ़ता जा रहा हूँ वैसे वैसे की नोट स्पीच का मैं टाइम लेता जा रहा हूँ. सो आई एम एक्सट्रीमली सॉरी फॉर दैट. थैंक यू मैडम.
Thank you, sir. As we progress through today's program, we have among us our chief guest, Dr. Manju Chattopadhyay, ma'am.
Ma'am is a faculty member with School of Electronics, DAVV University Indore since 2006. She has made significant contributions in the field of engineering, education and researches. Ma'am has published more than 45 papers in international journals and conferences. Ma'am is the recognized receiver for several prominent academic journals, including those of IEEE, Elsevier and Springer. Ma'am is also accomplished author with 4 books to her name and 2 copyright awarded by the Government of India. She conducts numerous workshops by delivered expert lectures. Ma'am has over a decade of experience as a course coordinator for various MTech, MSc, BSc course and those diverse range of subjects including embedded microcontroller, VLSI designs, methodology, network theory, ARMS and among others.
To express our profound gratitude, I would like to request Dr. Kavita Upadhyay, ma'am, Professor of Electronic and Communication Department, to felicitate our chief guest, Dr. Manju Chattopadhyay, ma'am, with sapling gesture symbolizing our gratitude for her presence and wisdom. Thank you, ma'am. Now, I would like to request Dr. Manju Chattopadhyay, ma'am, to uphold the dice. Welcome, ma'am.
Okay, good afternoon, everyone. I thank the coordinator and sir for inviting me over here. I have prepared a small presentation on these sensor devices that we have been working for quite some time. And this whole PPT is based on our paper which Kavita and I published in Elsevier Journal Material Science and Engineering B. With that time it had an impact factor of 4.7. So we initially, when Kavita joined with me, I asked her to do a extensive literature survey and publish a review paper on the sensors, because we were planning to work on analytical modeling of sensors. So that extensive survey, I think she covered almost 1,000 research papers, and out of which we cited around 500 research papers in our that review paper. So this whole slide is based on that one paper only, and it has multiple contributions from different published literature and other publishers. So my topic here is gallium nitride devices for sensor applications, and the focus area that we are working is 3V semiconductor device modeling. Device modeling is basically what we work is on mathematical modeling of the devices. We analyze the device parameters based on the material and their structure, size, and different physical parameters that are incorporated, and based on which the voltage, current characteristics and other behavior changes. So we do the device modeling using mathematical equations, and for that we need basic physical parameters, right? Okay, so the plan of talk is I'll be discussing the selection of the material, why we are choosing gallium nitride, then properties of gallium nitride which are specific for the sensor applications, common devices that we are using for sensors, the HEMTs, a brief about HEMTs, Schottky diodes, HBTs, LEDs and lasers, various sensors which are implemented using these structures, a brief overview of the device modeling, and a little about the work done by us, and what are the future scope of work and research aspects in this area. So what you can do, or okay. So selection of material gallium nitride. Gallium nitride is a compound semiconductor from 3V groups, group 3 and group 5 combination, group 5. From these groups we take materials and which are aluminum, gallium, indium, and we combine with them group 5 elements which are this nitrogen, phosphorus, arsenic and antimony. And we have 12 possible combinations. We can have binary combinations, ternary combinations, tertiary combinations, various combinations are there. And depending on those combinations, we can manipulate the band gap. Okay, so band gap manipulation gives us freedom to change various properties. The band gap that we want, that we can design. Okay, like silicon, we have only, what is the band gap of silicon? Huh? What is the band gap of silicon? Huh? So that is fixed. Okay, for germanium also that is fixed. Okay. So we have fixed band gap for silicon or germanium or other devices, materials if you are taking. Then, but for compound semiconductors, by changing the mole fractions of the intrinsic materials, we can change the band gap, and accordingly we can engineer the properties. Okay, so these are the combinations that we can use. So from group 3 we are taking gallium, and group 5 we are taking nitrogen. Okay, and what this gives us, gallium is basically metal. It is available in liquid form at room temperature, but if you combine it with nitride, it becomes a semiconductor. The combination behaves as a semiconductor, and it is a very interesting semiconductor. Okay, because of these intrinsic properties, that it has high critical electric field. High electric field means it can withstand high electric fields. Okay, so the device that you are forming, that can be that can work at high electric fields, high thermal conductivity, so it can dissipate higher heat. Okay, high power devices generate lot of heat, and that will, if the device is of high thermal conductivity, then that device can withstand the heat. Wide band gap it has, then high electron mobility. Faster mobility of electrons means, electron mobility we have studied, है ना, but electron mobility varies with different materials. Okay, for different materials the electron mobility is also different, because they have inherent scattering and all those, phonon scattering, ion scattering. Depending on them, we have a different electron mobilities in different materials. For this material, the electron mobility is high, so you can say that the electron moves faster, and then you can have eventually faster devices. Faster devices means they can work at high frequencies. Okay, and low dielectric constant. Capacitance is associated with our dielectric constant, and capacitance also is related to the delays, right? So if you have low dielectric constant, then the capacitance is lower, and eventually the delay is less. Okay, delay is less, so you get faster devices. So all these properties converge into high power density, high temperature applications, higher efficiency, reliable devices, and high frequency applications. So we can see that this is a table for material properties, and these for various devices, various semiconductors. Silicon is our basic semiconductor that we are using in CMOS devices. Then we had gallium arsenide. If you have studied microwave engineering, then you must have studied some devices based on gallium arsenide. So silicon to gallium arsenide was a faster working device, and it was used for higher frequency applications. Then we have silicon carbide based devices, and then gallium nitride. So if you see the properties of gallium nitride, these are much better as compared to other devices, and this there are various figures of merits and various standards are there to find out how we can converge all these and find a better device. So this Johnson's figure of merit, this is highest for gallium nitride, right? And then this is not a comma, this is a decimal. Okay, so this is for silicon, band gap is here somewhere here, arsenic here, and then gallium nitride has 3.5. Silicon carbide is closer, it is the closest rival gallium nitride has. And then in this also thermal conductivity, silicon carbide is the best, but closest one is gallium nitride, which has dielectric constant between 8 and 9. Okay, so high dielectric constant also. Lower dielectric constant leads to lower delay, and higher thermal conductivity helps in high power, high temperature applications. It also has a varied range of frequencies in which the gallium nitride can work. It is not showing here properly, actually the slide has changed a bit. This green portion is gallium nitride. So the gallium nitride works from like your 0.5 gigahertz to more than 100 gigahertz. It is working on these frequency ranges. And your silicon, this red one is silicon, which is up to only 1 gigahertz. And gallium arsenide, this is in your microwave range, 1 gigahertz to 100 gigahertz. So gallium nitride has the highest frequency range. Different substrates that are used with gallium nitride heterostructure, substrates are the base on which your structure is formed. Okay, so same device, same material is not necessarily needed for the structure, because the material on which you are making your device, that can be expensive or difficult to make such big crystal structures. So you have substrate of different materials sometimes, and the upper structure is of different materials. So the base that we use for gallium nitride, which is commonly used till now, is sapphire, low cost, available in large sizes. The base has to be available in large sizes, so your device is strong, but it has poor thermal conductivity, the heat dissipation is bad. High lattice mismatch with gallium nitride. So lattice mismatch causes, if lattice mismatch increases and you have big structures made one on another, it can fracture and your whole device can stop functioning properly. So lattice mismatch is a problem. Semi-insulating silicon carbide, very good thermal conductivity, good lattice match, but it is very expensive. Silicon based structures are also available with gallium nitride, but again it has high lattice mismatch, but the technology is stable, and we can have devices, we have many devices. The silicon industry is quite stable industry. N-type silicon carbide, that was semi-insulating, this is N-type. All things are good, but complex process of fabrication is a disadvantage. Then bulk gallium nitride, on which we form our structures. So it is a complex process, and it is very difficult to generate big crystal structures of gallium nitride. That is experimental part that the experimentalists are struggling with. Till now we saw that the gallium nitride devices are very much suitable for high temperature and high electric field kind of applications, high power applications. But recently, in last 10 years, it has been also explored widely for sensor applications. So how high temperature device can also be used for sensor applications, that is very interesting, right? And the properties that allow that is that it has exceptional chemical and physical stability. Whatever measurement you are taking, the device is very stable, very reliable. So material is stable, so the device is also stable. It has optical transparency. Gallium nitride is optically transparent. Very high two-dimensional electron gas that is formed because of spontaneous and piezoelectric polarizations. Okay, spontaneous polarization is that the polarization that happens without any external electric field, without application of any electric field. If the polarization is happening in the device, then it is called spontaneous polarization. So that polarization causes accumulation of electron charge at the hetero interface, and that electron charge is helpful in generating the current, high current. And there is also piezoelectric polarization, that is inherent property of gallium nitride, and because of these we have high electron gas formed at the heterostructure. High electron gas formation causes large current. Even if you have small change in the input, you have high electrons, high number of electrons. The high number of electrons means you are getting more current. So a small change is giving you big output. So you can detect the small change easily. So that is its inherent property. Large band gap, high temperature applications, these are also, these we have already discussed. Then environment friendly and bio friendly. Arsenic, like it is toxic. So if you use more devices based on gallium arsenide, you are spreading more toxins in the environment. But gallium nitride is bio friendly, it is not at all toxic. So for interaction between the living cells and the surface, there is quite feasibility, and they are bio friendly. Small sensing response time of milliseconds, you get the output within milliseconds. You don't need hours or minutes to keep that sensor in something to get the results. So the response time is very small. So common device structures used for sensors. First that we are working is a high electron mobility transistor. Okay, the electrons move very fast in this. First I will show the structure. This is the structure, basic structure. So these heterostructures were also formed by using aluminum, gallium arsenide and gallium arsenide. So heterostructures are basically formed by combining a material of wider band gap with smaller band gap. Okay, so this is aluminum gallium nitride which has wider this thing band gap, and gallium nitride has a bit smaller band gap than this aluminum gallium nitride. So when they meet at this junction, there is a band bending between them, and this band bending causes a what to say, well in which your electrons are confined. So they get fixed here only, and they don't move this side or this side. They can move only in this horizontal direction. So only two dimensions are there in which the electrons can move. So if you are confining your electrons in a channel and they are not scattered, then you are having more current. Okay, if the electrons get scattered, then your charge current is getting lowered. Okay, so this formation of 2DEG because of different band gaps of L-GaN and GaN, we have 2DEG here, and this causes a high two-dimensional electron gas. Okay, so they are confined in two dimensions, they cannot move in third dimensions. Also, the doping is only in this structure, L-GaN structure. There is no doping in gallium nitride. Your channel is forming in lower this thing, gallium nitride, and there is no doping. So there is no scattering also. So the electrons also move very fluently. They don't get scattered because of the doping ions. Okay, so this is the basic structure of HEMTs, and this you have drain, source, and you normally, like what you do in FETs, you use your gate voltage to control the this 2DEG, and you put voltage across drain and source to move the electrons, and you have a drain current. Okay, so but in L-GaN we have inbuilt 2DEG already formed, and the threshold is in negative, -3 or -4 you will have threshold. So without applying gate voltage, if you are applying gate voltage as 0 also, you are getting some current. Okay, so to remove the current, you have to apply some voltage at gate. Otherwise, even if you are not putting any voltage at gate, you are having current. Okay, just to move that electrons, you have to put suitable voltage at drain and source. So this is HEMT structure that we are using for sensors. Then Schottky diodes. Schottky diodes, as we know that Schottky contacts are formed using metal and semiconductor. For faster movement of electrons, free charge carriers. So here we have gallium nitride as semiconductor, and metals are used. So Schottky diodes, these are experimentally available diodes that people have fabricated. It is available in the literature. Heterojunction bipolar transistors, again we have an emitter, a collector, and base, and P contact is here, N contact, and P base is made up of silicon carbide, and your collector is this thing, and emitter is made up in gallium nitride. So these are different structures, LEDs, laser diodes, and this is the classification we have done based on the available literature, whatever sensor applications people have already implemented using gallium nitride in last 10 years. So it is used in radiation sensors, mechanical, biosensors, gas sensors, chemical sensors, and other very few sensors that has come up recently in high temperature applications, Hall effect, pollution monitoring platforms like the elements which cause pollution, nitrogen oxide, nitrogen dioxide, this, and then time of flight to measure the distance of a device, moving device, or to catch the speed of a moving car or something. For that also, time of flight, we are making sensors, and the concept of time of flight is used in them. Here in radiation, the gallium nitride is very resistant to any sort of temperature rise or this thing. So even for space exploration, there is a lot of iron radiation and all those things are there. So for those applications, the devices are made using gallium nitride also. So it is resistant, the temperature doesn't rise, and very less fluctuations are there based on all these. So it is used. Terahertz applications are above माइक्रोवेव माइक्रो का गीगाहर्ट्ज में होता है, इसका आपका होता है 14 12 12 तक की रेंज में जाएगा. एंड हायर द फ्रीक्वेंसी लोअर द वेवलेंथ, है ना. तो लोअर वेवलेंथ मीन्स यू कैन डिटेक्ट डिवाइसेस ऑफ लोअर साइज ऑल्सो. ठीक है. सो लोअर साइज मीन्स एक्सप्लोजिव्स एंड कंसील्ड एलिमेंट्स इन क्लोथ्स at airports and all. So those things can be detected using terahertz devices. So this is a very recent application that people are working on, and these are also used for biomedical applications like cancer detection, virus detection, small size element detection. Mechanical mein piezoelectric, piezo, it depends on the pressure. The pressure changes the electric current. Pyro is temperature to electric. Then dynamic stress and strain sensors. Again your pressure sensors. Okay, pressure sensors that are used for very harsh environments, chemically harsh or temperature wise harsh, or space में जो यूज़ होते हैं चीज़ें, वहाँ हार्श इन्वायरमेंट होता है. उन हार्श इन्वायरमेंट में स्पेशल काइंड ऑफ प्रेशर सेंसर्स आर यूज्ड इवन ऑफ द ऑर्डर ऑफ 6, मतलब 10⁻⁶ का पास्कल का आपका ये प्रेशर जनरेट हो रहा है, तब फिर आप कौन से सेंसर्स यूज़ करेंगे. सो ऑन दोज दीज आर यूज्ड in biosensing, which is also the topic for this FDP. pH sensors widely used. DNA sensors, botulinum toxin. This is the most poisonous thing that is there in the on earth. I think botulinum toxin. This is used in biological warfare and all those things. So the sensors, very sensitive sensors based on gallium nitride, have been developed using this. Glucose sensors for your wearable devices, sensing the glucose levels in the blood without invasion, just by touching through sweat or your tears or saliva. All those things can be used to detect the glucose levels of the body. Okay. Then virus, there was a paper which studied the presence of Zika virus. Using these sensors, they developed some system, and virus detection was also done, and that the slide can be changed, and the device transistor. So we were discussing biosensing, sensors, then gas sensors, various sensors. Hydrogen gas sensor hydrogen is used as a fuel in aerospace applications. So if the pressure is high or the concentration is not known, then it may explode also, right? So hydrogen sensors are there. Oxygen sensor, even if in a patient the oxygen is showing 100%, it doesn't mean that it doesn't have any carbon dioxide in it, requisite carbon dioxide. ठीक है. So oxygen का level maintain करने के लिए oxygen sensors रहते हैं. Nitrogen dioxide, it is a pollutant in it has to be monitored. Then CO, what is CO? Carbon monoxide, and it is known as silent killer. Why silent killer? Because we cannot detect, it doesn't have any bad smell or something. But रात को सिगड़ी जला के कभी कभी लोग सो जाते हैं, तो कार्बन मोनोऑक्साइड छोड़ता है. इनकम्प्लीट कंबशन कॉजेज कार्बन मोनोऑक्साइड, है ना. तो दैट इज़ वेरी पॉइजनस एंड इट इज़ लीथल ऑल्सो. सो टू डिटेक्ट दैट वी हैव सेंसर्स. Then CH4, H2S gases, different sensors are available. So radiation sensors, all these detectors for UV, I've already explained many of them. Terahertz detectors like For detection, mixing, even generation of terahertz, these kind of devices are used. And the fundamental plasma frequency, which is given by equation omega naught is equal to pi s upon 2L. L is the length of the channel and S is the speed of propagation. So for gallium nitride devices, for different temperatures, 300 Kelvin and 77 Kelvin, the critical frequencies at 10 terahertz and 1.6 terahertz respectively. But for silicon, we can see that we have considerably less frequencies, 1.7 and 0.46 terahertz. And gallium arsenide also it has lower frequencies at these two temperatures, 300 Kelvin and 77 Kelvin. So it has much higher critical frequency at terahertz range. Mechanical sensors, pressure sensors, strain sensors, and many advantages are there. Also the possibility for integration into MEMS and NEMS is there. I'll show some structures. I'm not going into equations of all these things, but you can remember this because we'll come later on this, how we mathematically derived these equations. So this is equation for piezoelectric polarization, which depends on the lattice parameters. This piezoelectric polarization changes with the pressure which is put on the device, and how we calculate that will come later. Different biosensors. So biosensors have two basic components. One component that converts the biological response into physical form, and another which converts this physical form into the electrical form. Okay, so these two components combine and make biosensors. So first of the applications one of the applications firstly, DNA sensors. This device has been fabricated by some of the authors. We have this combination of ALGAN and GAN, and the same 2DEG is being formed, and at the gate we see that there is no gate but only liquid which is having the DNA which is to be detected. That DNA is here, and this combination of the DNA varies the surface potential. To compensate for that surface potential, this 2DEG changes. So change in this 2DEG causes change in the current. Okay, so the change in surface potential is eventually reflected in the change in the current. That is how we are detecting the particular DNA. This is a similar device for this botulinum toxin detection. This has also been implemented, and we have taken this figure from the literature. So again, this gate has been removed, and this toxin is put here at the place, in the place of gate, and the surface potential changes cause change in the electron gas concentration, which is eventually we are measuring as the current. Glucose sensor, this is set up for glucose sensor. Here we have gate as reference electrode, some potential is provided, plus your glucose this thing sample is put here, and the change is basic concept everywhere is the same, that the surface potential is changing your 2DEG, and this 2DEG is very high, and so eventually it is resulting in high drain current. Okay, so the fluctuation that we are able to detect in all the sensors. So various sensors, size, combination, different things are used. So and this is also another setup by different experimentalists to detect the glucose. Another one for alcohol detection and APTS detection. pH sensors, here we have this gate sensing area where we are not using gate, and we are putting the liquid there, and same thing that the 2DEG changing. And pH sensor has various applications in medicines, bio, environmental science, chemistry, blood pH is around 7, and any change in this pH demonstrate that there is a change, the body is diseased. Okay, so pH is used in various applications. The concept is how we detect this pH change. is given by side binding model by Yates et al. And the MOH, where M is a metal, either silicon or something, and OH, this is split into MO and H plus ions. This MOH plus H plus ions result in MOH2 ions. This is happening at the surface. To compensate for this positive charge, the electrons accumulate at the interface and we have higher current at the interface. The sensitivity of pH sensors is explained as this: the change in current, drain current, with change in pH. So that this ratio is called the sensitivity of pH sensors, and these are the experimental setups that have been given by the experimentalists. Various gas sensors are implemented. Hydrogen sensor, I'm not going into details now as my throat is not working. Nitrogen dioxide, and this is another setup. Carbon monoxide, and chemical sensors for detecting the polar liquids and non-polar liquids. Polar liquids, where you have like water is a polar liquid, you have ions of the liquid in two different directions. Non-polar liquids, you can say that oil is a non-polar liquid, which so different types of acetone, ethanol, I think they are also polar liquids. For their detection, we have these chemical sensors, and these are various pollution monitoring sensors for lead, not only air pollution, soil or water pollution also is detected. Mercury, lead, cadmium, zinc, manganese. So many workers in India are also working on this pollution monitoring systems. Time of flight sensor, this is a sensor which is based on kind of, you can say, this is sonar mein karte hain ki sound goes and comes back, and then we detect how much time the sound took to reach there and get reflected. So similarly, like here we are using light from different sources, and the change in their phases, difference in phases is used to form a 3D object of the model. 3D model of the object is formed. So this distance will be 0.5 of speed of C and the time taken to reach there and come back. Okay, and these are A1, A2, A3, A4 are the different phases, 4 phases: 0 degree, 90 degree, 280 degree, 270 degree and 180 degree for forming the 3D model of the object. Hall effect sensors, 4 probe Hall effect sensors that we know, we have studied that. These are used for high temperature applications in the range of like 600 degree centigrade to 1000 degree centigrade. Silicon doesn't work above, maximum is 350 degree Celsius. Above 200 degree, it start behaving erratically. So for higher temperature sensors, we are using gallium nitride devices, and Hall effect, like 4 probe method, and all these are used for detection of temperature. This is the Hall voltage, which depends on the current and the direction of the magnetic field. This we have studied. So that concept is used to detect the temperature. Now device modeling, which we are working on, mathematical modeling of the devices. So why we do mathematical modeling? Because it is cheaper, and before going for fabrication and all, we need to do all the simulations and how the device will work, and we have to do all the studies before that. So mathematical modeling is much cheaper, and we can beforehand know the behavior of the device if we do proper physical or analytical modeling. So we use applied voltage, current, environmental conditions, temperature, radiations, etc. The sizing, doping levels, all these are considered, and the device behavior is studied. So modeling requirement is we select the suitable physical parameters, put in the equations, comparison of simulation or experimental data with our model. Usually we use the published experimental data, then we propose new structures for our proposed devices. Validation, if our simulation matches with the experimental data, then we accept the model we can then propose new devices based on that model. Otherwise, we have to redefine our model, change different parameters, include something, exclude something, some parameters, and then suitable model is generated. So this is a very basic 2DEG charge concentration equation, which depends on the dielectric constant, the charge, the distance from the top, applied gate voltage, threshold voltage, and the Fermi level. And this threshold voltage is again dependent on number of parameters, the surface potential, the charge conduction difference, that doping level, size of the spacer layer, electric field, and cap layer. This is polarization. ठीक है, शुरू में जो हम दिखा रहे थे, this is the polarization effect. All these has to be calculated to find the threshold voltage, and this threshold voltage is used to calculate the charge concentration. And then if we have the charge concentration, we integrated from one end to another end, we will get the current. Okay. So this polarization is further given by spontaneous polarization component and the polarization component Algan range in GAN range. 0 molar fraction is 0, so this is only gallium nitride. And here we have a different mole fraction for aluminum and different for gallium. So all these equations are available in literature, you can see that. And for IV characteristics, to conclude, we have charge density, polarization, threshold voltage, and mobility, and which further depends on different parameters, which is doping concentration, aluminum mole fraction, temperature, channel length, gate voltage, thickness, drain voltage, etc. We have done some publications with Kavita also. So these are the journals where we have published our work, and this kind of work is, as sir said, Rupesh sir, gives good publications in good high impact journals, but you have to work. ऐसे ही नहीं हो जाता है. You have to do lot of work, and then this is small work that we have done so far. और ये वाला पेपर है जिसमें से हमने ये सारी चीज़ें ली हैं. This is the base paper. Everything that I've shown in this slide is available in this paper. These are few more papers that we have published. And scope for future research, you can do analytical modeling of gallium nitride sensors depending on your choice, what kind of sensor you want to choose. We worked a bit on pH sensors. 3 papers we published on pH sensors, mathematical modeling. Not many sensors are there, so you can choose any sensor and work on that. Noise is also a big problem in the devices. So internal generation of signals that cause degradation from the desired response. So noise studies are also being done. Study of traps, effect of illumination on the IV characteristics, and the number of gates by increasing or decreasing or changing the shapes of the gates, that is also a study area. Multiple heterojunctions can be used. Here we have seen only one heterojunction where aluminum, gallium nitride and gallium nitride were combining. So multiple junctions can be there. So study of the effect of those multiple junctions can be the part of studies. Packaging for thermal management is also an interesting research area. And how to go for research? Simulation using TCAD tools. Sir has purchased many TCAD tools recently. You can take his help at IIT. By Silvaco or Synopsys, many simulation tools are there. Analytical modeling for theoretical predictions that we are doing mathematically, this can be done. And then fabrication process can also be explored. Like Government of India is doing these INUP classes and courses they are doing, and you get free facilities at IIT Bombay and IISc for fabrication. That is very, very expensive otherwise, and if you have suitable model and suitable device structure, you can go, you can approach them, IIT Bombay or IISc Bangalore, for fabrication of your device. Okay. So thank you, and thank you for bearing with me. Yes.
Is the formation of capacitance, whether we can say size of the capacitance, depends on the material what we are using for the fabrication.
Of course, capacitance तो डिपेंड करेगा ही. सी तो नॉर्मली आप देखें तो
रिसर्च ऑफ द गैलियम नाइट्राइड स्पेशली ऑन, तो अगर डिफरेंट देखें कि जो पहले थे और गैलियम नाइट्राइड में क्या डिफरेंस है साइज में, कैपेसिटेंस में, तो फॉर्मेशन ऑफ
कैपेसिटेंस तो जैसे आप सिंपल पैरेलल प्लेट कैपेसिटर लेंगे तो एप्सिलॉन ए बाई डी है, तो आप कितना विड्थ रख रहे हैं, कितना एरिया रख रहे हैं. एप्सिलॉन जो है वो गैलियम नाइट्राइड पे डिपेंड कर रहा है ऑफ कोर्स मटेरियल पे, बट विड्थ और एरिया वो सब पे भी डिपेंड करेगा. तो सीमॉस में जैसे हम स्टडी करते हैं, सिलिकॉन में भी स्टडी करते हैं, तो ए और डी वो करते हैं हम स्टडी. तो एप्सिलॉन जैसे दैट इज मटेरियल डिपेंडेंट प्रॉपर्टी. सो गैलियम नाइट्राइड का आएगा ना, फिर वो मोल फ्रैक्शंस हैं, डिफरेंट मोल फ्रैक्शन. अगर एल्यूमिनियम गैलियम नाइट्राइड आप ले रहे हैं तो मोल फ्रैक्शन डिफरेंट है, तो पूरा सबका अलग अलग एप्सिलॉन मिलेगा आपको. डाइलेक्ट्रिक कांस्टेंट कैपेसिटर भी सबका अलग अलग मिलेगा. तो दैट इज स्टडी कि अब बढ़ रहा है कि कम हो रहा है, कि इससे डिले पे क्या इफेक्ट आ रहा है. सो दैट इज
डिस्टेंस इज द मेटा डिस्टेंस पे तो है ही जो,
हाँ,
लेकिन मटेरियल पे भी डिपेंड करती है.
और डिस्टेंस भी आप मटेरियल पे डिपेंड होके ही चेंज कर सकते हैं. जैसे यू कैन नॉट मिनिमाइज योर सिलिकॉन डिवाइसेस बियॉन्ड सम पर्टिकुलर रेंज. तो गैलियम नाइट्राइड में कर सकते हैं, यू कैन हैव स्मॉलर डिवाइसेस. तो वो तो है हमारे पास. Yes.
Slide number 13 में जो था,
किधर से जाएंगे?
confined in a well. Slide number
ये नहीं, मैं पीछे जाएंगे हम 13 पे. 30 नंबर
13.
शुरू हो
मेरा
गया.
ये क्वेश्चन था कि लोग कन्फाइन हो जाते हैं वेल में, तो कैसे मतलब बाय डिफॉल्ट अपने आप हो जाते हैं कि किसी अदर वोल्टेज.
गैलियम नाइट्राइड जो स्ट्रक्चर्स है उसमें एक तो स्पेशलिटी है कि वहाँ पे पोलराइजेशन जो हो रहा है स्पॉन्टेनियस पोलराइजेशन हो रहा है, तो एक्सटर्नल इलेक्ट्रिक फील्ड की ज़रूरत ही नहीं, वो वैसे ही कन्फाइंड हो जाते हैं. सीमॉस में हम देखते हैं कि वी नीड गेट वोल्टेज टू कन्फाइन टू फॉर्म अ चैनल एंड ऑल. सो यहाँ पे उसकी ज़रूरत नहीं होती है.
यहाँ पे रेंज.
हाँ, ये 2D जो शो हो रहा है, ये स्पॉन्टेनियस पोलराइजेशन से अपने आप ही आ जाता है, बिकॉज ऑफ द मतलब इनहेरेंट पोलराइजेशन. उनका स्ट्रक्चर ही ऐसा है कि वो सारे वहाँ पे एक्यूमुलेट हो जाते हैं. दैट इज स्पेशलिटी ऑफ दिस हेट्रोस्ट्रक्चर बेस्ड ऑन दिस डिवाइस. और पीजो इलेक्ट्रिक पोलराइजेशन भी होता है कि स्ट्रक्चर के मिसमैच से या स्लाइट मिसमैच से भी वो पोलराइजेशन होता है. पोलराइजेशन मतलब द सेपरेशन ऑफ चार्जेस, तो द नेगेटिव चार्ज is getting accumulated there, and similarly positive charge is also accumulated at the other end, but negative charge है हमारे पास और उसको हम करंट की तरफ मतलब मूव करेंगे, VDS हम लगाएंगे, सप्लाई करेंगे तो करंट फ्लोज. सो दैट इज ऑलरेडी अवेलेबल. उसको रिमूव करने के लिए हमको गेट वोल्टेज लगाना पड़ता है. इट इज ऑलरेडी देयर.
एक्चुअली में क्या हम जनरली क्या होता है कि सेमीकंडक्टर इंजेक्शन बनाते हैं तो फ्यूजन होता है.
हाँ.
तो चार्ज मतलब आयंस रहते हैं, डिप्रेशन लेयर में डिपॉजिट हो जाते हैं. तो बाय डिफॉल्ट मतलब आप ये कहना चाहेंगे कि करने पे इलेक्ट्रॉन जो है वो डिपॉजिट हो जाता है.
हाँ, बिकॉज ऑफ दिस पर्टिकुलर टाइप ऑफ स्ट्रक्चर एंड दिस पर्टिकुलर टाइप ऑफ मटेरियल, इसकी वजह से ऐसा हो जाता है. सब में नहीं होता है ये सेम. आप अगर दूसरे डिवाइसेस दूसरे मटेरियल से बनाएंगे तो ऐसा नहीं होगा. तो गैलियम नाइट्राइड में ही हो रहा है. और गैलियम आर्सेनाइड में भी होता है ऐसा. गैस स्ट्रक्चर्स होते हैं, हेम्ड स्ट्रक्चर, उसमें भी होता था. पर फिर वही है कि वो लोअर फ्रीक्वेंसी पे काम करते हैं या हाई फ्रीक्वेंसी पे, उससे भी ज़्यादा हाई फ्रीक्वेंसी पे ये काम कर रहा है. स्मॉलर डिवाइसेस कैन बी फॉर्म्ड और हायर टेम्परेचर पे. तो हमने ये मटेरियल स्ट्रक्चर डिफरेंट लिया है. तो कुछ कॉम्बिनेशन है कंपाउंड सेमीकंडक्टर्स के जिनके हेटेरो जंक्शंस आप बनाएंगे तो ये प्रॉपर्टी आपको मिलेगी.
7 नंबर की स्लाइड पे मैंने जैसे वो फ्रीक्वेंसी और पावर का बोला था, तो क्या मतलब फ्रीक्वेंसी बढ़ाने से पावर कंजम्पशन कम हो जाता है? 7 नंबर की स्लाइड पे जैसे मटेरियल्स का आप देख रहे हैं, फ्रीक्वेंसी अपनी गीगाहर्ट्ज में बढ़ रही है तो पावर कंजम्पशन कम हो जाता है डिवाइस का कि
नहीं, ये उसके साथ रिलेटेड नहीं. ये है कि इतना ज़्यादा पावर पे इतना ज़्यादा फ्रीक्वेंसी पे काम करना है आपको, तो कौन सा डिवाइस मटेरियल डिवाइस सूटेबल है. ऐसा मतलब ऐसा नहीं है कि पावर बढ़ा रहे हैं तो फ्रीक्वेंसी कम हो रही है. आपको इस
बढ़ा रहे हैं तो पावर कम हो रहा है मतलब.
नहीं, वो इंडिपेंडेंट पैरामीटर्स है. पर आपको अगर इस फ्रीक्वेंसी पे इस पावर पे चाहिए तो कौन सा मटेरियल आपका यूजफुल रहेगा वो शो कर रहा है. जैसे अब आप गैलियम नाइट्राइड का देखेंगे ग्रीन वाला, तो ये इतना हाई पावर पे और इतना हाई फ्रीक्वेंसी पे भी काम कर रहा है. दूसरे मटेरियल्स उतना हाई फ्रीक्वेंसी पे काम नहीं कर सकते. तो दैट डिपेंड्स ऑन द मोबिलिटी, इलेक्ट्रॉन मोबिलिटी फास्टर रहेगा या और पैरामीटर्स जो है उन पर डिपेंड कर रहा है ना. मूवमेंट होगा आपका तभी हाई फ्रीक्वेंसी मिलेगी. अगर स्लो मूवमेंट है तो हाई फ्रीक्वेंसी एप्लीकेशंस नहीं हो सकता.
Yes.
अब ये सैंपल जो बना है, मतलब सेमीकंडक्टर बनाया है, आपने बनाया है कि
नहीं, हमने फैब्रिकेट नहीं किया, हम सिर्फ एनालिटिकल मॉडलिंग कर रहे हैं।
कि हम किस मेथड से करना है, क्योंकि मैं भी नैनो मटेरियल में काम कर रहा हूँ,
अच्छा, फैब्रिकेशन बेस्ड है आपका?
नहीं, वो मेरा हाथ सिंथेसिस प्रोसेस है और सब चीजें करता है। मैं बैटरी के एप्लीकेशन के पॉइंट ऑफ व्यू देख रहा था, या फिर सेंसर भी अगर डेवलप करना चाहते हैं तो फैब्रिकेशन कैसे हो पाएगा?
फैब्रिकेशन जो लास्ट मैंने आपको बताया ना, INUP प्रोग्राम है इनका, IIT बॉम्बे और IISc, उनको आप प्रोजेक्ट्स लिख सकते हो। उनके बहुत सारे वो प्रोजेक्ट पूरा साल चलते भी रहते हैं।
बेसिक थ्योरी पे तो काम करके पेपर भी अच्छे जर्नल में पब्लिश कर लेते
तो
हैं,
इसके
उसकी एप्लीकेशन जो मेरी ये है उस पे मैं कर नहीं पा रहा हूँ। तो
इसको फैब्रिकेट करना बहुत मुश्किल है, बहुत सोफिस्टिकेटेड डिवाइसेस चाहिए होते हैं। तो वो सब IIT बॉम्बे या मतलब उनके पास जो प्रोजेक्ट्स आते हैं तो फिर वो रिसर्चर्स के लिए अवेलेबल कराते हैं, और जो उनको ऑपरेट करने का एक्सपर्टीज है वो भी उनके पास ही। आप एक दिन जाके नहीं कर सकते, है ना? तो आप जाएंगे तो चिरी पिलानी में भी हो रहा है,
कैट में हुआ है,
कैट में हो रहा है, पर दे आर नॉट वेरी ओपन टू अदर्स। बट ये गवर्नमेंट ऑफ इंडिया का इनिशिएटिव है कि लोग आए और अपने प्रोजेक्ट इम्प्लीमेंट करें।
तो मैंने उनको रिक्वेस्ट किया था, तो बोला बहुत महंगी मशीन है।
हाँ हाँ, नहीं करते वो लोग परमिट।
मुझे सुना दी उन्होंने, फिर मैं
आप IIT बॉम्बे का जो INUP प्रोग्राम है ना, उसको जरूर एक्सप्लोर करें, नैनो फैब्रिकेशन।
प्रपोजल लिखना पड़ेगा।
हाँ, तो वो ट्रेनिंग भी देते हैं।
क्या रहेगा, कौन सी मटेरियल यूज करेंगे, क्या रहेगा, उनके पास होंगे तो वो अवेलेबल रहेंगे स्लॉट्स में, तो वो अलाउ करते हैं, अदरवाइज नहीं करते।
नहीं, उनके वो शुरू के इंट्रोडक्टरी प्रोग्राम्स रहे, फिर एडवांस प्रोग्राम्स, आप वो सब अटेंड करिए। वो करने के बाद वो दिखाते भी हैं उनके पास क्या क्या डिवाइसेस हैं, उसका पूरा आपको ये कराते हैं, टूर कराते हैं। देन उन टूर आपको वो दे नहीं देंगे कि आप बनाओ, ठीक है? आप प्रोजेक्ट बनाओ एंड इन देयर सुपरविजन यू कैन फैब्रिकेट। तो वो वैसे ही करना चाहिए, मतलब एकदम से हम लोग तो जाके वो तो कर नहीं सकते। हाँ, वो तो है, वो इनकरेज भी कर रहे हैं उसको करने के लिए।
One question is always arises in my mind, how far we can reduce the size of the semiconductor device, because generally the Ryzen processors are there which are generally based on 6 nanometers. तो कितना उसको reduce कर, because that directly impact on the power consumption. If the size is, अगर साइज को जितना कम करेंगे, that power consumption is also reduces.
सिलिकॉन में शायद सिलिकॉन बेस्ड स्ट्रक्चर्स जो है ना, उसमें आप एटम टू एटम मिनिमम साइज डिस्टेंस देखेंगे, दैट इज आई थिंक 5 एंगस्ट्रॉम। तो आप दो एटम्स तो चाहिए आपको एक डिवाइस बनाने के लिए। तो ये जो है मिनिमम डिस्टेंस जो है किसी भी मटेरियल का, वो ही डिफाइन करता है कि आप सबसे छोटा।
एटम का साइज कितना?
एटम का साइज वो मटेरियल पर डिपेंड करेगा। तो सिलिकॉन में जैसे 5 एंगस्ट्रॉम से नीचे नहीं जा सकते आप, वो उनका मिनिमम डिस्टेंस है बिटवीन द एटम्स। 2 एटम्स एटलीस्ट यू नीड कि यहाँ से इलेक्ट्रॉन्स निकलेगा, दूसरे पे जाएगा, है ना? आया कि नहीं आया वही आप डिजिटल कंडीशन जनरेट कर रहे हो। तो अगर दूसरा मटेरियल है तो वो, ये सारे न्यू मटेरियल्स जो हैं इसलिए एक्सप्लोर हो रहे हैं कि वी नीड टू डिक्रीज द साइज। सो सिलिकॉन कैन नॉट go beyond 5 angstrom. So for other device, for lower sizes you need to explore other materials.
मैं एक बार छोटा था क्वेश्चन होता, इसके लिए जो सेंसर एप्लीकेशन के लिए जो बैंड गैप की रेंज आप दिखाया था कुछ 3, तो 3 से ऊपर ही होना चाहिए, कम भी रहे तो
नहीं, बहुत चेंज कर रहा है। 1.8 से 6.4 तक जा रहा है, डिपेंडिंग ऑन द कंपाउंड यू आर फॉर्मिंग।
3.4
बहुत रेंज है उसकी, 1.8 से 6.4 तक थी। तो 3.4 गैलियम नाइट्राइड की, पर आप इंडियम मिक्स कर दो, एल्यूमिनियम मिक्स करो, फॉस्फाइड लगा दो, तो वो बहुत सारे आपको रेंज मिल जाते हैं। उसके सब थ्योरेटिकल सब है, बहुत एक्सटेंसिवली स्टडी किया हुआ है सब चीज़ें, ठीक है?
ये डिवाइस
हाँ, ठीक है।
सिल्वाको टूल उसका
नहीं किया, इसमें कुछ भी नहीं दिखाया मैंने सिल्वाको टूल का, पर लोग कर रहे हैं उसमें काफ़ी काम। दूसरा मेरा एक काम था, वो मैंने थोड़ा सा किया था IIT इंदौर में विश्वकर्मा सर के साथ, वो थोड़ा मेमोरी पे किया था हमने, उसका सिमुलेशन का काम, पर बस उतना ही किया है। तो अवेलेबल भी नहीं होता है वो ज़्यादा। अब सर ने परचेज किया है तो अब करेंगे सर के साथ काम। फैब्रिकेशन नहीं है, वो सिमुलेशन का था। TCAD टूल्स जो है वो सिमुलेशन के, वो बहुत एक्सपेंसिव है, टूल्स भी बहुत एक्सपेंसिव है। सिमुलेशन टूल्स जो रिलायबल सिमुलेशन टूल्स हैं, दे आर वेरी एक्सपेंसिव। तो ऐसा फ्रीली अवेलेबल भी नहीं है। वो है, बहुत सारे मेल वेल भी आते रहते हैं, बट पता नहीं वो एक्चुअली इतने अच्छे हैं कि नहीं। पर ये दो तो जो सिनॉप्सिस और सिल्वाको वाले, ये तो स्टैंडर्ड है, इंडस्ट्री स्टैंडर्ड्स हैं ये। तो आपको अगर मतलब सस्ते में अच्छा काम करना है तो आप मैथमेटिकल मॉडलिंग कीजिए। अवेलेबल एक्सपेरिमेंटल जो भी मिलता है आपको डेटा, उसके साथ कंपेयर करके देखिए। तो हमने बहुत किया है और अच्छे पब्लिकेशंस हुए हैं वो हमारे। और फैब्रिकेशन पे जाना है तो फिर वही IIT बॉम्बे, ISC इनको अप्रोच कीजिए या किसी के साथ कोलैबोरेशन कीजिए। ठीक है, चलिए, थैंक यू सो मच।